Polyglot Persistence. In this video, we'll explore the concept of using multiple database types for different requirements within a single application. You can see the icons of different databases such as SQL, document, key value, graph, and time series databases. So, what exactly is polyglot persistence? It is the approach of using different database technologies for different data storage needs within a single application. This approach recognizes that different types of data have different storage requirements. It matches data characteristics with the most appropriate database technology and optimizes for performance, scalability, and specific data access patterns. The core principles are selecting the right tool for the job, choosing databases based on specific requirements, domain-driven design, which means aligning database choices with business domains, loose coupling to maintain separation between different data stores, and pragmatic integration to balance complexity with practical benefits. Let's take a look at some common database types. First, we have relational SQL databases. These are for structured data organized in tables with predefined schemas and relationships between entities. Use cases include structured business data, complex transactions, and data with clear relationships. Next, we have document databases. These store data as flexible, semi-structured documents typically in JSON format without requiring a fixed schema. Use cases include content management, user profiles, and evolving data structures. Then we have key-value databases, which are a simple data structure that stores data as a collection of key-value pairs with fast lookups. Use cases include caching, session storage, and user preferences. We also have graph databases, designed to represent and store data as nodes, edges, and properties to model complex relationships. These are useful for social networks, recommendation engines, and fraud detection. Time series databases are optimized for storing and querying time-stamped data points collected at regular intervals. These are useful for Internet of Things sensor data, application monitoring, and financial market data. Finally, we have column family databases, which store data in column families, optimized for queries over large data sets with high write throughput. These are used for event logging, content management systems, and high-volume data storage. What are the benefits of polyglot persistence? There are key advantages to it. Firstly, optimized performance where each database type excels at specific operations, allowing for better performance for different data access patterns. Improved scalability as different database technologies can scale independently, based on their specific workload requirements. There is also flexibility to adapt to changing business requirements by selecting the most appropriate database for each new feature. Also, domain-specific solutions where matching data storage to the natural structure of different business domains within the application. Then resilience, since failures in one database system don't necessarily affect other parts of the application. There are also many business impacts as well, such as faster time to market, develop features more efficiently by using databases that naturally fit the data model requirements. Cost optimization by using expensive specialized databases only where they add value, and simpler solutions elsewhere. Also, better insights. Leverage specialized query capabilities to extract more valuable insights from different data types. Enhanced user experience to deliver faster response times and more relevant features through optimized data access. Finally, future-proofing is adapting to emerging data requirements without complete system redesigns. Like every other methodology, polyglot persistence has its own challenges. Let's discuss those along with possible solutions. One of the challenges is data consistency, while maintaining consistency across multiple database systems with different transaction models. The solution is to use event-driven architecture using event sourcing and message queues to maintain eventual consistency between databases. Another challenge is integration complexity, as in connecting multiple databases with different application programming interfaces, query languages, and data models. The solution is to use abstraction layers by creating service interfaces that hide the complexity of underlying database interactions. Next challenge is data duplication and managing redundant data across different database systems, while keeping it synchronized. The solution is to use bounded contexts by applying domain-driven design to clearly separate different data domains and their storage needs. One more challenge is learning curve, as in teams need to learn multiple database technologies, query languages, and operational practices. Knowledge sharing solves this problem by implementing cross-training, documentation, and specialized teams for different database technologies. Another challenge is monitoring and debugging, while tracking performance and troubleshooting issues across diverse database systems. Unified monitoring can solve this problem by implementing centralized observability platforms that can track metrics across all database systems. Here is a reference architecture, a modern Polyglot Persistence implementation. At the very top, we have the application layer. This layer consists of user portal, analytics dashboard, e-commerce platform, and mobile app. Under the application layer is the service layer. This layer has user management, search and recommendations, product catalog, analytics service, and transaction processing. At the very bottom of this diagram, we have the database layer. This layer consists of PostgreSQL, which is a relational database, MongoDB, which is a document database, Redis, which is a key-value store, Elasticsearch, which is a search engine, Neo4j, which is a graph database, InfluxDB, which is a time series database, Cassandra, which is a column family database, and Simple Storage Service or blob storage, which is an object storage. Here are some implementation examples, code patterns for Polyglot Persistence. Starting with the repository pattern. Here we define a generic repository interface with methods like find by ID and save. Then we provide an SQL implementation of this interface. Moving on to service abstraction. Here we have a user service that uses both a primary repository and a cache repository. It first tries to retrieve the user from the cache, and if it's not available, it fetches it from the primary repository and saves it in the cache. Let's examine some real-world case studies. The first one is an e-commerce platform. A large online retailer implemented Polyglot Persistence to handle diverse data requirements across their platform. Their database stack included PostgreSQL, MongoDB, Redis, and Elasticsearch. They used relational database for orders and inventory, document store for product catalogs, key value for sessions, and search engine for product discovery. They achieved 40% faster search response times and 99.99% availability during peak shopping seasons. The second case study is a financial services. A banking institution implemented Polyglot Persistence to balance transaction integrity with real-time analytics. Their database stack included Oracle, Cassandra, Redis, and InfluxDB. They used relational database for core banking, column family for high-volume transaction logs, key value for session management, and time series for market data. They reduced fraud detection time from minutes to seconds, while maintaining ACID compliance for critical transactions. The third case study is gaming platform. A multiplayer gaming service used Polyglot Persistence to handle diverse data needs with high throughput. Their database stack included MySQL, MongoDB, Redis, and Neo4j. They used relational database for player accounts, document store for game state, key value for leaderboards, and graph database for social connections. They scaled to support 500,000 concurrent players with sub-100 millisecond response times for critical game actions. Now let's explore some best practices and future trends. Starting with best practices, choose databases based on specific business requirements, not technology trends. Align database choices with well-defined domain boundaries in your application. Implement robust event-driven mechanisms to maintain consistency across databases. Use repository patterns and service layers to hide database implementation details. Implement comprehensive observability across all database systems. As for future trends, machine learning systems that automatically recommend optimal database types for specific workloads. Single database systems that support multiple data models, such as document, graph, relational, within one engine. Fully managed, Auto-scaling database services that simplify polyglot implementations. Advanced tools for maintaining consistency across different database types with minimal code. Standardized security frameworks that work consistently across different database technologies. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.